All right, so now let's suppose that we have our NOT gate, but this time, when we replace a transistor, we replace it with two transistors in parallel, meaning that their ends are connected to each other's corresponding ends. And no surprise, this is a NOR gate given my title here. So let's just look at each configuration. So we got could have two zeros, a 0 and a 1 and a 0, and two ones. So let's see what could happen here. So if we have two zeros, what we kind of have is an open connection and an open connection, in which case ground cannot get to this point, and so the positive voltage wins and we get a connection like that, and their output is a 1. Now if we have a 0 and a 1, that means this guy's open, but this guy here is closed. So really, this ground has two paths that it could get to its output. And so it's kind of a little goofy, but that's what we end up with, because this is a much stronger connection to ground than this connection is to 5 volts because of the resistance there. And doesn't matter if we flip them around, it still works the same way, where this guy's closed and this guy's open. And now 0 can get to the output like that. So sorry, I should say we got a 0 here, 0 here. And last but not least, we've got two ones, which means that this guy's closed and this guy's closed, which really means we could get ground to the output two ways, but we still get a 0. It doesn't make it extra 0 or anything like that. It just still is just 0. And so just real quick, recapping our truth table, if we just say it doesn't matter A or B, it's commutative. So we've got 0, 0, 0, 1, 1, 0, and 1, 1. So if we have all zeros, our output's a 1. If we have a 0 and a 1, either way, the output's a 0. And if we have two ones, the output is a 0, which this is a NOR gate.